Hi, some of you wanted a bit more explanation of addition reactions. Which occur with double bonds. So if we consider the double bond, so we've got an alkene here with a carbon, double bond to carbon, and we're going to add to it some hydrogen, so some H2. This in reality would require a catalyst to perform. We don't need to worry about that when we're looking at the equation. Now the way I'd look at this is when we're going to react with an addition reaction, this double bond here is going to get broken. So what I'd do is I'd look at my hydrogen molecule, and that consists of a hydrogen single bonded onto another hydrogen. So as I say, that double bond is going to get broken, and one of the hydrogens is going to go onto one of the carbons, and the other hydrogen is going to go on the other carbon. So we're going to end up with, oh, I probably should have put the other bonds in there. Now, because this double bond has broken, we've got 3 bonds, four bonds around each carbon. So we're going to add the hydrogen here and here. We can repeat the process with another different molecule here. So if we've got the carbon to carbon double bond in our alkene, and maybe this time we're going to add some bromine, like we did with the bromine water when we were in class with the alkane. We could have carried on and done the alkene. This reaction's a lot quicker, and the bromine water changes from orange to colourless almost immediately. Okay, so if we consider the bromine molecule as a bromine atom single bonded to another bromine atom, and this time this bromine atom here is going to bond onto this first carbon, this other one is going to bond onto that second carbon, and this double bond here is going to get broken. So we're going to end up with a carbon to carbon single bond, and whatever was attached to these other bonds still stay there, but now we've got a bromine on one end of the now single bond, and another bromine on the other end. Okay, so if we go for a third example, again we'll draw our carbon to carbon double bond, and we've got our whatever's attached to it here, and this time we're going to react it with Cl2. So again, same as we did with the bromine, we've got a chlorine atom single bonded to another chlorine atom, and this double bond is going to break. One of the chlorines is going to bond onto one of the carbons in the double bond, and the other chlorine is going to bond onto the second carbon. So we end up with a carbon to carbon single bond, our bonds that we had already, and then our new bonds with the chlorine atoms at each end of the double bond. Now these 3 examples are all examples of symmetrical, small symmetrical molecules. And the product, we only get one product from small symmetrical bonds because there's no other place for each of the atoms to go. But if we have a look at the asymmetrical molecules, and there's just 2 that we need to worry about, we'll see that there could be 2 possible results. So for these two examples, I'm going to give a specific molecule to react with. So we're going to react our molecules with propene. So CH2, double bond, CH, single bond, CH3. And if I draw this out as a Lewis diagram, I'm going to have carbon, and my hydrogens here, I've got my double bond, carbon, hydrogen there, and CH3 here. And I'm going to start off with HCl, so I'm going to react this with HCl. Now, if I write this out in this HCl molecule out in the same way as I did the previous ones, I can write it as it's written there, hydrogen to chlorine, like that. And if we look at it in the same way as we did before, this double bond's going to break, this hydrogen is going to bond onto this carbon, and this chlorine onto this carbon, and we end up with, I draw this in a green arrow because I'm going to show you something else in a different colour in a moment. So for the green arrow, we're going to end up with a carbon and 3 hydrogens, single bond, then a carbon, hydrogen, our CH3, and our chlorine. Now there is another possibility for this molecule. So if I choose, blue. So if I could instead have my hydrogen and my chlorine round the other way. So I could have my chlorine on this side and my hydrogen on this side. And instead of the hydrogen bonding onto this first carbon, I could have the chlorine atom bonding onto this first one and the hydrogen onto this second one. And this would produce this product. So we'd end up with our carbon with our 2 hydrogens on them. But this time we're going to have our chlorine on the first carbon. Then we've now got a single bond because our double bond is still broken. We've got our carbon bonded to our hydrogen and our CH3 attachments, but then we've got our hydrogen on this molecule. So if we try and name these two molecules, here we've still got 3 a carbon chain. So we've got prop. Oh, let's write this in green because we've got prop. And it's now an alkane, so it's a propane. It's got a chlorine atom attached, so, and that's on carbon number 2, so this is 2-chloropropane. The other product we've got here is, again, 1, 2, 3. We've got 3 carbons, so that's propane. And our chlorine atom, I should have done this in blue, shouldn't I? Our chlorine atom is on the first carbon atom. So we've got 1-chloropropane. So we've got 2 different products here. Now there was a Russian chemist who came up with a rule about, he did a lot of study of these type of reactions, and he found that this product here, the 2-chloropropane, was the substance that was produced in the majority, and he called this the major product. And by definition it's about a 3-to-1 ratio. This is our minor product. And the way we describe it is that the carbon that has the most hydrogens to start with, so this carbon here has got 2 hydrogens, and this carbon here has just got 1 hydrogen attached to it. So the carbon that's got the more hydrogens on it is more likely to get the extra hydrogen atom. So the hydrogen-rich carbon gets richer, and the hydrogen-poor atom doesn't get the extra carbon.